This is the test mass, which is at the heart of the LISA-Pathfinder and LISA apparatus.
LISA-Pathfinder is really pushing a boundary of all technologies we need to fly for LISA. So LISA is a brand new concept and nothing has ever been flown before.
We have two test masses which are not moving very much with respect to each other inside the spacecraft, inside their vacuum cans. And what we do is measure their separation on a very fine scale of 10 to the minus 12 of a meter. So it's a very, very small distance in their separation.
It's demonstrating that you can do stillness at the level which is required by gravitational wave detectors.
So to do that, we build an interferometer which sits in the middle and reflects light off both of these optical test masses, and we use that reflected light to infer the distance between the two of them.
The concept of getting as free fall as possible of the test masses in LISA-Pathfinder is that everything else has to follow the test masses, including the spacecraft.
We can take this gold platinum cube, put it inside a spacecraft, and then fly the spacecraft around the gold platinum. The little cube doesn't follow the spacecraft follows the test mass.
You have a test mass which is shielded by the satellite, and so it doesn't feel the solar radiation pressure or residual drag, which instead act on the satellite. The satellite is then controlled with a set of high-precision micro-thrusters to follow the test mass. In flight, this test mass will be free-falling inside of a capacitive sensor like the one you see here. As you can see, this is made of a conducting Faraday cage with a set of electrodes. These electrodes are used for measuring the test mass motion in all degrees of freedom, and this is used then for the control of the satellite.
We need something which has got a very high density, but a very low magnetic susceptibility, a magnetic signature. So that's a pushing the boundaries on metallurgy.
This is a 2-kilogram cube made of gold platinum, which is chosen because it's very heavy, but also because it can be made very pure, free of any magnetic impurities, which would create stray forces on the test mass motion.
The first release of the test masses was the most exciting moment. So we were retracting the fingers that were holding the test masses with a huge force, and we didn't really expect that they would float afterwards, but really for minutes they were floating freely, and we couldn't take our eyes off the monitors.
Certainly this was very tense, because you have to think that releasing the test mass is almost the same as launching the satellite, right? You're putting a body in orbit, right? And if that fails, the mission fails. So this was a magic moment.